Thanks for joining. I'm Sébastien Gonzalve, so I will present myself quite quickly because I don't have a slide for it. I've been working in a startup that was writing a distributed storage system for quite a long time now, and since then I changed quite a lot of job, but I worked also for a huge company in the semiconductor industry, doing some audio stuff. And lately, I joined an automotive company, and I'm working on embedded systems in there. If you want to get in touch with me, there's my email at the end of the talk, and you could even Google me. I think you will find me quite easy. So this talk is about safer multithreading with C++. It's based mainly on my experience through the years. So there are quite a lot of people using threads in their application. And I must say that I saw many times many problems when trying to refactor things or just trying to figure out what was going wrong. So this talk is a way to give you clues, maybe to help writing your code with multithreading better, or maybe just discover new things if you don't know anything about threads. So maybe I can start with asking people to raise their hands if you are currently working on an application that uses threads. Okay, so for now it's quite a few, so it could be great. So let's go on with it. So let's start with the kind of problem I often see when I get into some hunk of code I don't know yet. So this could be anyway. So this could be in a far, far away galaxy, whatever. So you get this kind of code with a function that gets a version and returns a version. So far, so good. It's supposed to be a string. So okay, let's do it. In some other place, there is a config that is passed to this function out there, and it's doing something quite astonishing at first sight. It's just waiting for the config and perform a get version on this object called this function and wait for the string to be returned as an empty string. And when the string is empty, then we sleep 10 seconds. So here is quite astonishing because either this is monothreaded and this will probably just deadlock because here who will set this string while we are sleeping here if it's not multithreaded? And if it is multithreaded, then how do we see the synchronization between the threads? How this line is supposed to work when this version is set? Who is protecting the access? So you may find such things in many places, and that's the main point of this talk, I think. So let's see with threads. So why is thread? So here is a quote from Alan Cox. It may that states that the computer is a state machine, and a thread for people who can't write a state machine. So this may look quite rude at first sight. Let's remember that this is a kernel, a Linux kernel guide. So in kernel, threads are not, well, you have to write the code that makes the thread work. So maybe you don't want to use your proper stuff just to run it. But mainly, it was a time when the machine did not have really multi-cores, and having thread was just making scheduling between tasks on the same core in the end. So there was no real parallelism on those machines. So yes, looking at state machine was already a good idea. Here is another thing that states that multitasking is screwing up everything at once, and it may end up like this. Yes. So as I just said, yes, writing a state machine may be easier, and probably if you are using quite a lot of threads, you should have a look to what you are doing and maybe trying to think about reducing the number of threads. Maybe sometime you may use a state machine. It's much easier to debug because there is no concurrency. When you put a breakpoint in the state machine, you get exactly the state you have, and you can you don't depend on timings. This is really interesting. That said, sometimes writing a state machine is quite hard because they may become very huge, and when you get very complex state machine and you need really asynchronous stuff, maybe having threads is really necessary, and especially if you want to exploit more than one CPU at the time. So if you have really separated flows in your code and you have low interaction, yes, it could be a good idea to spawn threads just to separate things. And I have this job done here and this one here. Another way in which it could be interesting is transforming blocking operation into asynchronous operation. If you have some thing that is known to be quite long to be computed, or IOs, or I don't know, and you don't want to wait for them, but it's basically a blocking call you have, you can use a thread just to perform this blocking call and then get the result later. And you may also rely on this to get better latency reaction, meaning that if you have one thread which job is just waiting for answering as quickly as possible to an event, it may be useful to have it dedicated to this task and not performing some other task meanwhile. And the last one is parallelization of code, because now we have very huge CPUs and many cores and many performance needed, especially for games or videos or whatever. You may need to perform real parallelization of your code, parallelizing your algorithm. And yes, here threads are really relevant. Thread and C++, actually, before C++11, threads were not part of the language, and it was even stated. So here is the quote from the standard that the abstract machine representing the code running for C++ prior to 11 was fundamentally single-threaded. On the other hand, since C++11, now it's multi-threaded by design, because as many people were using threads and using libraries, relying on them, we needed to have something built in the language to make sure that things were behaving correctly while during the execution of your software. Prior to 11, it was working, but more because the compilers were doing their jobs and stuff like this, than because the language was allowing it. So it relies a lot of the memory model. We'll talk about it later. But now it's coming. It came in C++11, and you may do threads inside the language itself. So how to create threads? You may already know it, but it's just as a reminder here. You can use stud thread. So this is a C++11 way, and there are a new way to do it in C++20. You can create a JThread. So the auto join. That was the main problem with threads even prior to event, but especially in events that you need to join your threads when they finish or detach them. But it's generally not a good idea to detach them, I would say. So. The other way to create a thread in C++ right now is using async with the launch policy async. If you do not specify the launch policy here, you may not have a thread spawned. So if you really need a thread to be spawned, you need to add this one here. But you may also use third-party libraries. So maybe you already use the pthread libraries or create thread on Windows. But for code parallelization, you may also use OpenMP or OpenCL, etc. That spawn thread as well. This slide is about the challenges of multithreading. One must remind that distributing data is not that difficult. The problem is about synchronizing the result in the end. So if you spawn many threads and just say, okay, you do that, you do that, you do that, this is really simple. You may see that just in the way of your commits in your project. If you are using something like Git to handle your patches, just creating branches is not difficult. Merging things is difficult. So here is the point in the same way for threads. So keep that in mind. Just distributing is not difficult. Another point here I put is the law of Demeter. So one would like the user of its object not to know about its internal, so that it's easy to make this class evolve without exposing its guts. So having threads coming out or synchronization things coming out of your APIs is usually a bad idea, because you expose the fact that you are using threads on multiple core or things like this. And maybe if you want to go back in the future, it will be a problem for you because you will need to completely break your API, and so your clients will need to do so as well. And the last point is that parallelization has limits. So the nice thing is that there was a talk about performances yesterday, and this graph was already shown to you. So we had the same one. It's the Amdahl's law, which is printed here, which showed that depending on the amount of parallelization you have in your code, the speed up is not really relevant sometimes. So here we can see that if you have only 50% of parallelism in your code, even if you have a huge number of cores, the speed up will be quite low. It's less than 2. Having a parallelization of 75%, which is not quite bad, is only 4. So keep that in mind. Sometimes we say we just multiplicate the number of cores and parallelize my code, etc. If your code doesn't get really parallelized, you won't be able to gain any performance. And even here, you see it's 95%, and above 100, it's not really useful anymore. And mainly, the main reason for Amdahl's law to have this is that in the end, you need to share results between threads, and this causes bottlenecks anyway. So the main point is about concurrency. So let's get deeper in this. The problem of concurrency are races. So races is just like those people running. You have many threads doing their jobs, and they are going in their own speed, let's say, and they will probably do the job in a way you can't predict, and maybe the result will happen in a non-deterministic way. So races per se are not really a problem. But the problem arises when you have race on data, which are called data races, and this is making problem. So data races are the races that happen when many threads are trying to write at the same place in memory without synchronization or with poor synchronization, and so one cannot really predict in which order the result will be accessed, so either in read or either in write, and this is making problem, especially it is stated as undefined behavior by the standard itself. So if you have data races, it's a main problem you have in your program. So here I insist on the fact that races are not the problem per se. The problem is about data races. So here the link on Wikipedia if you really want to have more about this, but I guess many of you already know that. So let's sum up what we saw. If you have non-shared data and they are constant, yeah, it's okay. There is no problem in here. If you have constant data that are shared, still there are no problem either, because as they are constant, access in memory are just accessing always the same data, so it's just okay. If you don't share things and modify them, well, it's just like single threaded things, so it's still okay. But problem come when you are trying to have mutable things and sharing them. So this is where the problem arises, and the little cat is not really happy here. So how do you get evidence about races, especially data races? Usually, people fill them when they are running their CIs or things like this, because they say, well, sometimes there are some random behavior in the test, or the CI is failing for some reason. We don't know really. So it's one time on 50, so it's not really problem, but it happens sometime, and no one really knows why. Sometimes you get data corruption. You write something somewhere, and quite astonishingly changes its value, or you read it and you read it again and it's not the same value, but you don't really know why. So these are evidence you can experience as a tester or user, let's say. And you may and should probably use tools to detect them, especially if your software is using quite a lot of threads. So there are two kinds of tools. They are static analyzers. So here are some examples of them. So Coverity, Code Sonar, Clockwork. There's a presentation about Code Sonar Cube, I think this afternoon. So these are tools that are looking at your code and just trying to figure out at which point you may encounter data races or any other problem, let's say due to parallelism. They are working quite correctly, but sometimes they are not enough, and there are other tools that are dynamic analyzers, so they are running at runtime. So I put them here, maybe the two ones that are mainly known. So Valgrind, especially with the Lgrind tool. So Valgrind per se is mainly looking for bad access in memories, but there is a special tool called Lgrind you may activate, and that will spy your program at runtime. And then try to figure out if there are races, and especially data races in your code. Valgrind does not need your software to be recompiled. It doesn't expect anything. It just run Valgrind in your program. You can also use a lib sanitizer. So this needs to be added at compile time. So you may enable this switch, special with thread. You may know it for memory or address. So this one is for thread, and it's performing quite the same analysis than Valgrind. It's just instruments your code and look for places where data are accessed without synchronization mechanism. So here is a little piece of code showing an example of race and data race. So here is the main where I spawn, in fact, 2 threads. So an NB threads is 2 at the top of the program. So I spawn 2 threads, and what they are doing is they are doing a race. They are just looking to reach a max number and just increasing a global variable, which is the score here. So until they get the score at certain values, they increment it. And when this value is reached, we just print I'm the winner. So what I say here, when the number of threads is 2 here. On my machine, I have 2 winners. Both are here and say, I am winner. 2 lines printed like this. So it could be quite awkward at first sight. And when I put a bigger number here, there are no more winners. So the issue here is that the access on score is not synchronized or protected in any way between those threads. So here, the tests that are here and the while and as increment here are doing things that are wrong. One here I put a note about putting atomic on them, and it would not solve the problem. I won't spend too much time on it. If you need an explanation about this, so this won't fix the race, the atomic. It will fix the correctness of access of memory. So if you put an atomic here, there is no data race per se, but your algorithm is still wrong. Maybe if I have time, I'll come back to this the late slides. So here is the report given by the thread sanitizer report. So here is the code I copied back on the slide, so it's really the same. And here is the analysis. So the red part were added by me, but here is the real result I get when running on my machine. And you see, it's really helpful. It says almost everything you need to know. So you can see here, it says there are 2 threads. They say where they are spawned, actually. And it reports what are the problems. So here it says there was a read of size byte at this address, okay, from thread 2, and it's a problem. So this happened at line 10 in my sample program. So here is the read that caused problem. So it says, okay, when you read score here, there was something wrong with this read. And there was a race with line 11. Yes, from thread 1. So we can easily understand here that, yes, for sure, incrementing the score while reading it in the while loop has some unexpected behavior, let's say. So to solve this problem of data races, we must rely on synchronization primitive so that when you are accessing the data from many places, many threads, you are sure that what you read is correct. So there are several classical synchronization mechanisms, especially on Unix. It's the same for Windows, but I know them less, let's say. So there are semaphores. You can use system file semaphore or pthread, etc. You may rely on messages. Messages allows you to keep ownership, exclusive ownership in your code. So each thread receives a message holding the data, but it has exclusive access on the message. So you may do that with an external library that passes message through your threads, or implement it via FIFO or sockets if you like low-level programming. Simple signaling could be achieved with signals. So you may use system file signals or RT signals or any other signaling method you use. Nevertheless, in C++ 11 and above, we are invited to use higher level concepts because all this is working and worked a lot in the past, but they are very clumsy at use, and it's very error prone because there are a lot of corner cases to take into account. And when you just want to have single communication between threads, you may use a higher concept that comes with C++ 11, and maybe especially future, so that you don't handle all this by hand. So here is a slide on the futures in case you don't know them yet. Future are handy mechanism to separate the computation from the place you wait for the result of value. So you create a promise. You can take the future link to this promise. So here, the example of pseudocode I wrote is about matrix multiplication. I just say, well, I will do a multiplication. The future will represent the result of this multiplication. So I get the future from the promise I created just above. And then on one thread, I wait for the result. And then I get the result. And the other thread is the one that is performing the computation and makes a big matrix computation. And there's typo here. So this may take time and very long time and may also be parallelized in some way. And when this is finished, the value is set and the future is complete. And then this line stop blocking and can resume in here to get the result. So here is a very simple example because I call wait, so I'm getting blocked. So this would defeat the fact that I want it to be asynchronous. But I'm not forced to wait here. I could say I do some other stuff, and regularly I looked the future if it's complete or not. That said, future have limitations and make it quite difficult to use in some cases. So the first one is maybe not the most important, but they cannot be used in a signal under. So if you want to signal something with your future from a unique signal, you won't be able to do it. You cannot reuse a future. You cannot. There's no kind of reset in the future. You cannot say, okay, I received this result, but I want to reset it so that it can be set again. This is just not possible. You have to create a new future and overwrite the previous one. There's a side effect of creating future with async. So the policy launch async when the destructor of the future is called. If the async is not complete, you get blocked. And mainly, this is mainly the biggest problem, in my opinion, is the fact that you cannot wait many futures at the time. So it was more or less planned to come as stud when any and stud when all in the C++ 20 at a certain time, and it was dropped because people in the committee decided to go to a higher level of abstraction to perform those many waits. So for now, you don't have such mechanism. So you may use a boost that has some identical things available. The drawback is that you won't be able to use to the future. You would have to use a boost future. So if it's not a problem in your code, you may do that. But since then, it's a problem. So here I just state again that using stud async is not enough to have asynchronous stuff. You need to launch it with async. Then when you just discard the futures as a solution for your code, then you need to rely on something maybe lower level to perform synchronization, because this is nice in some situation, but maybe not always, usually not always. So let's see what we can do with other tool. At first, I just want to talk about volatiles. So the short answer about volatiles and synchronization is that it does not help. It's very common to see code that using volatile as a magic bullet in a multi-threaded code just to have some kind of synchronization, and this does not help. So the long answer is here. Volatile are mainly used to, in case you have things modified in a signal handler, for example, you need to put them in a volatile. And when you are accessing a special memory, so if you are running on a special hardware that is modifying the memory underneath, and nothing is aware of it in your OS or software stack, you need to put this. But here it states clearly in the standard. So here are quotes from CPP reference. You may find them here. They are not suitable for communication with another thread of execution. And within a thread of execution, there is no guarantee that the order is correctly observed by another thread. Okay, and since it does not establish inter-thread synchronization, so this is a really important thing. Let's go on. Here is a slide about atomic. So the nice point is that yesterday there was a nice talk about Felipe about atomics. So it will prevent me to have a lot of explanation here about atomics. You may refer to his talk. So if you want more details, there are many details in his talk. It's really interesting, and it really explains how atomics are working. So C++11 provides atomics. That's new. Formerly, you didn't have such things. You were maybe needed to write assembly code to perform such operation. Now it's in the standard, so this is a nice thing. And yes, it could help communicating things between threads, because atomic operation are guaranteed to be atomic, which means that you cannot see an intermediate state while modifying them. So either you see the previous value, or either you see the new value, but you cannot see in between. That said, there are quite a lot of limitation, let's say, with the use of atomics. The first one, and the main one, it's really hard to use to write a correct algorithm using only atomic variables. It's a huge task, so it can be done, hopefully, but it's really hard to do. Prior to C++20, it was not possible to notify and wait on atomic values. So if you need such tools, it was just not possible using C++, the standard one, let's say. It is important to understand that a bunch of atomic variable is not atomic itself. So if you just put together many atomics, they don't behave all together as one atomic, and this is usually the source of many bugs. And usually they are really useful and efficient for native types of your hardware or your OS. If you try to use atomic on a bigger structure, which is possible with libatomic, in fact, you don't really use atomic operation from a CPU point of view. And here I remind what I already told you, that using atomic does not make your algorithm working all the time. It just prevents you to have data races. So this is important because adding atomics may remove reports from the tools as being problematic, but you may encounter still races in your code. And maybe it's badly behaving just because there's a race. So it's not undefined behavior, but it's not working anyway. So the main synchronization mechanism you may already all know, and that is widely used, are locks. So locks allow to perform safe concurrent access on data, which means you can access, you take a lock, it blocks every access on it. I can read the data associated to that is protected by my lock, and then I can release and everything's fine. Here I insist on the fact that you should lock data, not code. How is this working? It's taking advantage of memory ordering that was introduced in C++11 as well. Please go see the presentation of Felipe, because he explained this really in deep. So here is a bad summary, I could say, but the memory ordering allows you to perform some kind of atomic commit in memories. I mean, you are able to say, well, from now I want everything that I wrote in memory to be committed. So if it was in some kind of cache somewhere, it is now really in the main memory and shared. And on the other hand, you may say, now I'm about to read, so I want in the same way to make sure that everything I will access will be the correct view of the thing, so all the cache were written, etc., etc. So here I say is a bad summary of the presentation of Felipe. I really invite you to see his presentation. It's really really interesting, and explain this in deep. So here are manually locking things. If you really want to have some common pattern, and if you are just locking data without signaling, you may use a pattern like the monitor pattern that is presented in this talk of Herb Sotler. So it's really interesting because it just provides some kind of template use to access data. The limitation here is you don't have signaling with this pattern. So here I just want to insist on what is a deadlock. Probably you already know it, but worth explaining it again. A deadlock happens when there are many threads, and some threads want to access in an exclusive manner to resources that are taken in an exclusive manner by another thread. So here is the example. Thread 1 has an exclusive access on resource 1. Thread 2 has an exclusive use of resource 2. And thread 1 wants 2 and 2 wants 1. And this is deadlock because in order to get this exclusive access, I would need thread 1 to release his access he's got, but it won't do it until it gets the access on the second one. So here is the most simple deadlock we may encounter. They may be really tricky. When I worked on distributed system, it was also across many machines, many CPUs. This can be really tricky to detect, but some tools may help you to detect them. About locks and array. C++ and C++ core guideline especially insist on the fact of using resources with array, and locks are resources, as you get a resource through a lock. So you are really invited to use array to handle your locks, and the standard provides you a way to handle them with array. So mainly you will use log guards, unique lock, and scope log. So let me detail what they are doing. So log guard is an object that takes the lock on the mutex you provide it in constructor and release the lock you provide in its destructor. So when you create such an object on your stack or anyway, you have the guarantee that when this object is finished to be built, you have the lock. And if it gets destroyed for whatever reason, so let's say exception or whatever, the lock will be released, and there won't be any downlink deadlock waiting in the code. Unique lock are more or less the same thing. The only difference, let's say, is that you may be able to unlock manually a unique lock, which is not possible with log guard. Log guard, you must destroy it to unlock the associated lock. And scope lock is a new class. I can't remember. I think it's C++17. It was introduced. That allows you to lock many locks always in the same order. So if you take the previous example here, this is a naughty pattern of locking. You should always take locks in the same order, which means here there's a bug in the code. Thread 2 should have tried to take the lock 1 first and then the second one, so that the deadlock would not happen, because here this blocking here, the thread 1 would not be possible. So this is something already well known by people using lock in general, but usually they are doing it by hand, by reviews, or making sure they do it in the good order. Here is an object that does it for you, and so you don't have to care. Just say, take my logs, log them in the right order, and I just don't care. I just put a note here about a reverse lock that is provided by Boost. That is more or less the same mechanism as log guard, but it's just doing the contrary. You give it a locked lock, and when constructing the object, it will unlock the mutex you provide, and when it is destroyed, it relocks the mutex you provided. This could be interesting if you want to temporarily read the lock. For example, here calling a blocking function. Maybe we'll see that in the next example. So here is an example of fishy locking. So something's wrong in here. So I don't know if you people have an idea of what's going wrong here, but let's get through it together. Here I have a function that takes a callback, that takes a lock, okay, seems to protect these members, that sets the callback to the value. So callback should be some kind of function, and run, which must be some Boolean, is set to true. Okay, so far so good. And here I see that we launch a thread, and in this thread we access mrun and mcb, but there is no more lock in there. So here it's half locked, let's say. The callback is protected here, but then we just run it without caring of locking. So is this lock really needed, or is this just wrong? It should take the lock and check if run is true, holding the mutex. You may see also this kind of stuff with log guard around the call of async here, which is quite useless because the locking does not happen inside the lambda here. Another example of fishy locking. Here I have a function that is called a set context. So all these examples are some kind of real life example. I'll reward them a bit, but I found them in real production code. So here is about setting a context from a unique pointer. Okay, we take the lock. Okay, just move the context, right? But later there's a function called get context, which takes the lock. So far so good, but unreference the pointer and return the context. And here is something strange. How do we know that when we set this context, this reference here will remain correct? One cannot know actually. So here, what is being protected is the pointer itself. It's a unique pointer itself, which is named context here. But the data pointed by this pointer is not protected. So we provide the user an object that may be destroyed at any time. And I guess the guy that wrote that thought the locking was correct, but here it's quite fishy and probably wrong. So let's come back on synchronization and signaling. Usually we need to signal things between thread. So some thread is performing some computation and need to tell the next one that his computation is finished. So the main tool for doing that is using conditional variable. It involves three things. You have a bunch of data you want to monitor. You have a lock associated to those data, and then you created the condition variable that is working with both of them. I insist on the fact that any missing premise of when using a conditional variable is very likely a bug. If you have code with conditional variables and you are missing something of this one in your code, you are very likely having a bug. And especially if you are using atomic things, thinking the lock would not help in your case. It is clearly stated in the standard that you must take the lock when modifying the data in order to have the notification published on the other thread. So this is important. Usually with Conva, you are calling the wait function in some way at some time. I really recommend you to use the predicate signature. So this one is just waiting, holding the lock. But the problem is this function may have spurious wake-ups. It means that the OS may wake you up at any time for any reason while it was not really signaled. So you have to find a way to make sure you were woke up for the real reason. And the way you make sure you were woke up for the right reason is using this predicate here. So you pass here a lambda saying, I want to sleep until this predicate is true. And then you are afforded to be awake on the right reason. This means, as a consequence, that any things that are used in the predicate should be either immutable, so maybe constants, or immutable from the place we are using it, either protected by the mutex you are using here. If you modify things without using this mutex, the predicate won't behave correctly. And the second consequence is that if you change your data in some way, you should probably have a notify called on the condition variable just following your code, because it's the only way to make the predicate evaluated in the end. So here is a bad use of conditional variable. So the point is that I have two mutexes, and I on one thread use one mutex, sorry, and another I use the other mutex, and this is not working because I may be able to miss wake up here because the mutex was not the correct one, it was not the same one, and so the notification here may be simply not seen at all. And even if the code is set to the correct value, then the lambda here won't be evaluated because we just didn't see the notification. Here is another bad usage of condition variable, especially using atomic. So I already told you that using atomic with a condition variable is usually useless because you need to use a mutex. So here I just put this job that is waiting for stop and stopping and loading stuff just to check if it's needed to be stopped. So I take the lock, I just check if I can stop, and then I go in the lambda waiting. Here is my predicate. And in the main, I just say, okay, I spawn my job. I notify for some reason the convar. Then I simulate here some work. And then I set stop to true. It's atomic, so it's okay. There's no need to lock. And I notify. And this does not work. At least it doesn't work always. So it may work sometime, but there's a race. And you may see the race by adding this simple line here, slip in the evaluation of the predicate. What's happening here is this notification triggers the evaluation of the predicate, but the predicate is taking a long time now. And here, the second notification happens before the evaluation of the predicate has finished. So the framework just say, I'm just evaluating the predicate right now. So I don't need to remember there was a new notification. If the former notification was about to stop the process, it will stop it. And mainly because it should be using a variable that is locked by the mutex. If here I consider the lambda uses is evaluated with the mutex locked, it should not be possible to change the value when notifying. But here, as I don't take the lock and I just rely on the atomic stuff, I create this race. This is a pattern I saw quite a lot of time while debugging code. Here is a live example and a Goldbolt if you want to have a view of how it's working. So here is a report given by Helgren about this race. So it just says there was no lock held while storing things, and there was a lock held while doing the load on the value. So it points quite accurately what was the problem. So just use tools. Next bad one. So here I have two booleans and two mutexes for each one, but I share the same condition variable. So this could be nice. Even it's maybe not a good idea to share the same convar. But so here I set the value, I take the lock, I change the thing, and here I'm waiting on code that is with the correct lock, so should be okay. But the problem is here is I call notify one. I just notify only one thread waiting on this convar. And unluckily, there's another thread waiting on this convar, which doesn't have anything linked to code in its predicate. Here, I'm just looking for quit to change. And if I'm not lucky, this will notify this wait. It will evaluate this predicate, just say it's not yet the end, so we'll turn back to wait. And this one will never get the notification. So that's another point. I have care about notifying one or all threads, and maybe not share too much your convar, even if your locking is quite correct. So some correct pattern of using those convar should be something like this. You got a mutex, you got a convar here, some data associated, and on one thread, you take the lock, you change your value, you notify one or all, and in another thread, you have something waiting for the predicate on this data to give a certain value. with the lock L. But this, you don't have the choice. To be able to call the wait, you will need this unique lock to be here. This slide is about managing contention. So usually people say, well, I don't like lock because there are a lot of contention. If you protect data and only data, the contention should be low. Remember that a CPU can run billions operations per second. Even if you spend quite a lot in flashing memories or making memory barriers, it is really, really, really fast. And especially for 80% of code you may write. But one may care not calling blocking function while holding the lock. So you should constrain yourself to take the lock only when changing or reading the data, and any function call, and especially IOs, should be done, if possible, on copies that do not hold the lock. Make sure you split your data and lock so that you don't get a very big amount of data with a single lock. So for those who remember, there was something like this in the Linux kernel at one time, the big kernel lock. And it's just awful because as everybody is trying to take these locks that locks everything, there are contention everywhere. So you better split in a little part your data and associate them the log that is just taking care of those data. Keep in mind that there may be allocation you don't see. So there was a talk about performance yesterday. It was stated as well. Remember that growing a vector or things like that may allocate memory. So if you do that holding a lock, it may be a problem. So maybe you should use reserve prior to adding something to a vector, for example. In any case, if you think you have contention or you want things to go faster, measure your code, measure, in order to make sure you don't get optimizing times on locks in places where there are no contention at all. If you have many reader and few writer, you may use a shared mutex that is provided by C++ 17. So here is an example. Shared mutex allow you to say when you are accessing in read, you may read at several threads at the time. And it's getting really locked only when someone is trying to write. So if you mainly read stuff and rarely write things, you should look at that. It may be useful in some situation. So we are reaching the end. Keep in mind that you need to challenge your code when you are using thread and especially lock. Imagine that you may have 10 seconds between each line of your code. So you should have a working software, deterministic outcome, even if you put sleep in each line, unless you are doing timing things. But if it's just event controlling, you should not have any issue by adding sleep anywhere. If you release your lock and you take it back, the value may have changed 100 times. Don't think, oh, I just unlock for a few seconds, it should be the same data. No. If you want the data to remain the same, you just have not to unlock. But once you unlock the stuff, it may change 100 times, so you cannot say anything about its value. The last point is about writing a lock-free algorithm. Here, the link points to Herb Sutler talk about making a lock-free algorithm, which calls juggling with saws or something like this. It's really, really hard to write, and if you really need it, you should have real reason to do it. So you should have measure that you need to do it, and then you have to take really extra care about how you write it, because it's really hard to write and it's really hard to debug. And so here are some takeaways. We'll go quite fast because we're reaching the end. So prefer high-level things whenever it's possible. So I think future or even other mechanisms, if you can have them from other libraries. The more thread you have, the more complex it gets. So keep in mind that each time you create a new thread, you are adding complexity in your code. So you should keep the number of threads as low as possible. Try to hide your thread inside your object, which means that usually people don't need to know that they are async stuff or things like this. So hiding them in your behind your interfaces, or you to change the implementation, maybe add more threads or remove them without impacting your client. Keep in mind that data races are important, so you should fix them. It's not just a problem of consistency; it's just undefined behavior. You should use tools to detect your threads, your races, log data and not your code, so that it's easy to check if each time you access the data, you have a lock. And especially if you put this data as a private member in a class, all logs and data will be in a single CPP file, and it's really easy then to see if the lock are correctly taken. And that's all. So the closing quote is from Brian Kernighan. Don't forget that debugging is twice as hard as writing the code. So if you are to write the most clever thing you can, you won't be smart enough to debug it.